So this video is a continuation of the anomalous Zeeman effect. So on that last video, we were talking about spin orbital coupling right here. From the electron's point of view, the proton goes around him, giving him a magnetic field, and he's spinning. And these two couple together, giving me this as the energy right here, which we derived last time. And S sub z and L sub z are not good quantum numbers because they're not constant. So what we do is we define the total angular momentum, L plus S, and it's this that's constant and the z component of it that's constant. So now all we care about is the total angular momentum and the z component of the total angular momentum, and we're going to use J for that. Matter of fact, they use J even if you have multiple electrons, multiple spins. J is always the total angular momentum of everything. Okay, and they work just like L and S would. Same with the J sub z, and M sub j goes from minus J to plus J. Now, we did say on the last one that J, the maximum it is L plus a half, but then it drops an integer, and we didn't know how far down it went. But then we looked at that vector, and we got some vector relationship that said this had to be greater than this. So let's just look at it now for some specific cases. Let's look at it for the case where L is equal to 0. For L is equal to 0, that means that this up here is that J can be 1/2, minus 1/2, minus 3/2, ... We don't know how far it goes. But we'll get that from right here. Now if we plug in what L is, and we know what S is 1/2, we get the square root of J times J plus 1. It's got to be greater than or equal to, L is 0, so that whole thing is just 0. Minus, but we're doing the magnitude, so that's just a plus. It's the square root of S is 1/2, 1/2 times 3/2. Okay, now all we have to do is figure out which one of these will work. Well, if we plug into this one, we get 1/2 times 3/2. Well, that is greater or equal to square root of 1/2 plus 3/2. So that looks like, if I pick one that's smaller, it's not going to work right here. So it looks like for L equals 0, the only one that's going to work is this one right here. Can't have them complex in there. So let's look at the next case for L equal to 1. For L equal to 1, that means from up here, J can be 3/2, 1/2. Sorry, when L is equal to 1, that's 1/2. That's going to be negative 1/2. ... Okay, and so now if we plug in back into this formula, we got the square root of J times J plus 1. It's got to be greater and equal to, well, L is 1, so that would be 1 times 2 square root of 2 minus, that's 1/2 times 3/2, which is the square root of 3 over 2, which is 0.866 magnitude right there. Okay, well, what is this thing right here? If you subtract that out, that's 0.54. 0.54 after you take the magnitude of that. So now if we come over to here and we say, okay, does 3/2 work? Well, if you plug in 3/2 here, you get the square root of 3/2 times J plus 1, which is 5/2, which is the square root of 15 over square root of 4, which is square root of 15 over 2, which is 1.9. 1.9. That works, so that one will work. if we plug in the 1/2 into here, 1/2 times 3/2 is the square root of 3 over 2, which is 0.866. So that one will work right here. But not the third one, because we'll be a negative number over here, and you can't get a negative in there. So for L equal to 1, we have these two. What about L equal 2? Let's just go over here. L equals 2. That means J can be 2 plus 1/2. That's 5/2. 2 minus 1/2, which is 3/2. And then 1/2, and then minus 1/2, and so on. Well, now if we come over to this, the square root of J times J plus 1, it's got to be greater or equal to. L, we said, was 2, so we got 2 times 3, which is the square root of 6, minus, and remember that one is always going to be the same, 0.866, 0.866. Okay. This is, if you plug that in, that's 1.58. Okay. So if we plug in the 5/2 here, that's gonna be greater than 1.58. If we plug in even the 3/2, that was 1.9. So that one is going to work. But if we plug in the 1/2, that's 0.866, which is not going to work. So only these two will work right here. Matter of fact, as long as, if I kept going up to L equal 3, only the first two will always work. So what the rule is first of all, when L equals 0, there's only one solution right here. That's just L plus 1/2, which means that if L is 0, it's only 1/2. J is 1/2. When L is not equal to 0, for all the other cases right here, then it just looks like it's the first two terms. It's always the first two terms. It's L plus 1/2, J equals L plus or minus 1/2. So that's what J can be right here. So now let's just go through our states here for a minute. We already know, let's look at our form. First of all, where n equals 1. And I want to know, actually I'm going to bring it down just a little bit. N equals 1. I want to know what the L is, the M sub L, the M sub S. That was the old way we did it. But now the new notation will have a L, we'll have a J, and an M sub J. And the notation, remember we said L determines an SPD orbital, and N is usually out in front, but usually when they're using spectroscopic notation, they like to use like this. They put the N sub L, N superscript in front, L sub J right here. So I'll put the notation in this last one. Notation. Okay, so for our n equal 1 state right here, L can only be 0. That's all it can be. M sub L can only be 0. M sub S is always plus or minus 1/2. So there's plus 1/2. Actually, I'm just going to say plus minus 1/2. So there are two states right here. There's 1, 0, 0, 1/2, 1, 0, 0, minus 1/2. So the degeneracy is 2. So I'll put that in parentheses right there. Over on this side, L is 0. We already said L is 0. When L is 0, j can only be a half, so j is 1/2, and m sub j, we already know, goes from minus j to plus j. So it goes, there's two of them, there's plus or minus a half, plus minus 1/2. There are two states here, 1, 0, 1/2, 1/2, 1, 0, 1/2, minus 1/2. The notation would be like this. It'd be n, which is 1. Then the L, which was S. And then sub j. Well, j is just 1/2. So they would write it like that. 1s, 1/2. The m sub j isn't in the notation right there. Okay, well, let's look at the n equal 2. Well, L can be 0, because L can be anything 0 or 1, so it's going to be 0, and this has to be 0, and you get plus or minus 1/2. There's also, L can be 1, m sub L can be, sorry, I don't need to write m sub L. M sub L could be 1, or 0, or minus 1. And this is plus or minus 1/2, plus minus 1/2, plus minus 1/2. Okay, that gives me 2, 4, 6, 8 possible states here. 8 possible states there. Now, what would they be on this side over here? L can be 0. If L is 0, J has to be a half. M sub j is plus or minus a half. Okay, and that would be called the 2s 1/2. 2s 1/2 state. Now, L can also be 1. Sorry, L can be 1. Well, when L is 1, J can be either 3/2 or 1/2. So I'll pick the 1/2 first. J can be 1/2. So this can be plus or minus 1/2. Or it could be 3/2. And M sub J now can be 4 things. M sub J could be 3/2, 1/2, minus 1/2, minus 3/2. Okay, and these states right here would be 2p. This would be the 2p 1/2, 2p 1/2. And these down here would be the 2p 3/2, 2p 3/2. If you look at how many states we got here, you got 1, you got 2, 4, 5, 6, 7, 8. You've got 8 states there. They have to have the same number of them right here. Okay, well, let's go to n equals 3. Well, you can get L equals 0, 0 plus or minus 1/2. Over here, this is going to also be 0, 1/2 plus or minus 1/2. This state would be the 3s 1/2. Okay, then we could also get the 1. This would be 1, 0, minus 1. And you could have 2 with the 1, sorry, the 2, 1, 0, minus 1, minus 2. And each one of these has a plus or minus a half with it. Plus or minus 1/2, dot, 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 all the way down. So the total number of states is 2, 4, 6, 8, 10, 12, 14, 16, 18. 18. I should be able to get 18 steps over there too. For the L equal 1, it's going to follow just like these did. You get the 1/2 plus or minus 1/2. That would be the 3p 1/2. Then we'd have 4 of these states where you had 1 and 3 halves. So you'd get 3 halves, 1 half, minus 1 half, all the way down to minus 3 halves. These all would be the 3p 3 halves. Then L can be 2. If L is 2, if L is 2, J can be, let's do the minus first. 2 minus a half, which is 3 halves. So J can be 3 halves. When J is 3 halves, we get all these states, 3 halves, all the way down to minus 3 halves. How many does that give you? Gives you 1, 2, 3, 4. It gives you, there's 4 states there and there's 4 states there. Okay, and then you also get, and those would have been the 3, at 3D, 3 halves. 3D, 3 halves. And then we would have had the other case here where you had 2 and 5 halves, because it can be plus a half. And now you're going to get 5 halves, 3 halves, 1 half, minus 1 half, minus 3 halves, minus 5 halves, which gives you 1, 2, 3, 4, 5, 6. 6? 1, 2, 3, 4, 5, 6. Yeah, you got 6 of them. These would be the 3D 5 halves. Now, we said there was a total of 18. We better have 18 over here. You got 6, you got 4, there's 10, another 4, which is 14, 15, 16, 17, 18. So, you still get the same, it has to be, you're just labeling them different right here. So these are the notations when you have the spin orbital coupling right here. Okay, well, now the only thing we haven't done is when we calculated the energy right here, we haven't figured out what the energy, how much does it shift it by right here. Remember, we said before, whenever when we said something about perturbation theory. Perturbation theory. When you're changing the Hamiltonian, which is H, and you're adding a minor change to it, plus, say, some H1, where this is a small effect right here. And when you're operating on your psi equals E, now your E is a little bit different. It's what it used to be, plus some delta E psi. Normally, when you solve this all out, you would get different eigenfunctions because psi only worked for H and E. It didn't work for this other stuff in there. But we said to a first approximation, if we wanted to calculate delta E, all we have to do is sandwich in to our psi just the H1 and whatever we're perturbing it by psi. That's all we have to do right here. That's all we care about. We just want to know what is the energy shift right here. So what do we have to do? We have to, remember, this is just the integral. So delta E would be the integral. It's really 3 integrals because you got to integrate over r, theta, and phi, but we're just going to write it as 1 integral. And then my h. My h is this right here. Now I can bring out all the constants out in front. That's a constant. That even s dot L is a constant. The only thing that's not is this right here. So I'm going to pull all the rest of that out. So we got G sub s. Actually, over here, since G of s sub s is 2, and that's 2, I'm just going to cancel those 2 right there. So we got mu b over mc squared h bar e mu b, actually I'll put the integral in yet, mu b all over mc squared h bar e, and then I'll even pull out the s dot l, and so we'll just have to integrate psi, and the only thing left inside is 1 over r du dr. Psi star. And you're integrating over r theta and phi. Let's just say the volume right here. Actually, I don't have to integrate over the volume because there's no theta in this and there's no phi in this. So really, I'd only have to integrate over the r. Remember, I'd have to put an extra r squared in there, but I don't want to do that yet. You'll notice this is just the expectation of 1 over r du dr. That's all it is. Why don't I just keep it like that for now? So that's all it is. So it looks like delta E, how much the energy is shifting from what we get from the Bohr, is mu B all over mc squared h bar E. We got this term, I'll just write it here next, 1 over r du dr, and then we have s dot l. Okay, so how do we, first of all, calculate S dot L right here? Well, remember the definition of J. J is equal to L plus S. Well, suppose we did a J dotted with a J. J dot J. Well, that's equal to L plus S dotted with L plus S. J dot J is J squared. And over here, if we just FOIL this thing out, we got L dot L, which is L squared. And we got the last term, which is S dot S, which is S squared. And then we got the middle term. You got an L dot S and you got an S dot L. Well, the order doesn't matter, so it's just 2 times S dot L plus 2S dot L. Or I can get the S dot L out of here. S dot L is this minus this over 2. So it's J squared minus L squared minus S squared all over 2, or we know what J squared is. S dot L is equal to, this right here was H bar squared J times J plus 1 minus H bar squared L times L plus 1 minus H bar squared S times S plus 1, all divided by 2. All divided by 2. So I do know what that term is, right here. We'll plug in, we know what S is, that's 1/2. It looks like I could pull out the H bar squared and cancel with one of these, but we'll wait a second. Now let me calculate what this is. 1 over r du dr. 1 over r du dr. Remember what this u was, that was the potential between the electron and the proton. We know what that is. U between the electron and the proton, it's minus E squared all over 4 pi epsilon naught r. So there was our U. Remember, we got that from the force between the electron and the proton. So now, if I were to take the derivative of this with respect to r, du dr, Well, that would make it a plus over r squared. It would make it an e squared all over 4 pi epsilon naught r squared. Okay, and now putting that in, it would make it an r cubed on the bottom. So if we wanted to calculate 1 over r du dr, what do we have to do? We only have to integrate over the r because the theta and the phi's, they would just become 1. They're all normalized. So we're just integrating over r from 0 to infinity. I guess I'd have to pull this out in front, this e squared all over 4 pi epsilon naught. So we get, remember, it's psi star, well, r star, be just our r star times what we're trying to, it would just be a 1 over r cubed because we have an r squared there and another r, so you got 1 over r cubed times r. And then with our volume, we have an r squared dr. R squared dr. Okay. Well, this thing right here, if we were in the ground state, it would be easy to integrate this thing out right here, but it depends on both n and l right here. And if you work this thing out right here, this just becomes 1 over r cubed. We did 1 over r when we did it before, but if we had just made it 1 over r cubed, what it comes down to is just 2. I'm not going to work it out right here, but because we'd have to do it for all the states and see how it depends on n and l, but it would be a naught cubed. Got to have a length down there. That was the Bohr radius. N cubed L times L plus 1 times 2L plus 1. Okay, so that's what we'd get if we plugged in right here. Okay, so now I can go ahead and I can plug everything into this delta E right here. How much our energy is going to shift by. So delta E is going to be mu B. I think I'll even turn my mu B back into remember, this was the Bohr magneton, which is EH bar over 2m. So that's EH bar over 2m. So that's mu B. All over mc squared h bar E. All over mc squared h bar E. Times this term right here, which is this times this. So we got an e squared all over 4 pi epsilon naught times all of that, which was this, 2, all over a naught. A naught, that was our Bohr radius. What was the value of a naught right here? I think I have it written down. If you remember our Bohr radius, I didn't want it in the answer, so it's 4 pi epsilon naught h bar squared all over me squared. Okay, so I'm going to have that cubed. So I get a 4 pi epsilon naught cubed h bar, if that's cubed, that's h bar to the 6th. H bar to the 6th all over m cubed e to the 6th. All over m cubed e to the 6th. Okay, that takes care of that. And then we have an n cubed. N cubed. L times L plus 1 times 2L plus 1 Okay, that takes care of all of this term. And then we still have this one down here, the S dot L, which is h bar squared over 2. I'll factor that all out. H bar squared all over 2. And we get j times j plus 1 minus L times L plus 1 minus, and then S is really a half, so this is just a half times 3 halves. Half times 3 halves is 3/4, minus 3/4. Okay, this 2m, I can really bring it down to the bottom. It just sort of, it's 2m right there. Okay, let me see if I can combine most of this stuff together here. There's an E here and an E there, and that's gone. There's an H bar here and an H bar there, and that's gone. There's a 2 here and there's a 2 there, that's gone. There's an M and an M cubed, so that would just make that M squared. Okay, so let me rewrite that. So delta E is equal to M squared e to the 8th power also we have an H bar squared and H bar to the 6th, so I think that just means an H bar to the 4th down here. So there's just a 4, and that's gone too. So let me see, I think that's the entire numerator, M squared e to the 8th. Okay, and down below we have that right there. Well, we have a 4 pi epsilon naught to the 4th. We have an h bar to the 4th. We got a c squared. And this m, I guess there was another m right there. Yeah, because that came from the 2m. So I guess that's only m to the 1 power, because there's m squared there, and we had m cubed. So it's just m right there. Okay. Just wanted to share. Okay. And there's a 2 in the bottom too, right there. There's another 2. Okay, so I think we've got it all right there. And then we're left with j times j plus 1 minus L times L plus 1 minus 3/4 divided by n cubed L times L plus 1 times 2L plus 1. I think that's it so far. Okay. Now, if you remember, just to simplify this a little bit, remember our fine structure constant, which is 1 over 137. That was just E squared all over 4 pi epsilon naught h bar c. And we also had our Bohr energies, E sub n, which we said was the minus 13.6 over n squared. But if we put it in terms of all the letters here, it was minus m e to the 4th all over 2 times 4 pi epsilon naught squared h bar squared n squared. So that was just what we got from the Bohr right here, which was the same in quantum, and here was our fine structure. Suppose I were to say, what is alpha squared times E sub n? What if I squared this and multiplied it by that? What would that give me? Well, this thing would give me, actually, let's say what is minus this times this give me? So now, when I multiply that, the minus, this will be positive over on that side. But we get E squared times an E squared squared, that's E to the fourth, times another E to the fourth, that's E to the eighth. We've got M, there's no M over here, so that's just M. Down below, this squared, 4 pi epsilon naught squared, times another, that's squared, so that's 4 pi epsilon naught to the fourth. Then we're squaring this, that's h bar squared, times that h bar squared, that's h bar to the fourth. And then, what else do we got here? I think C. We got c squared, but there's no n over there, so it's c squared. And then the only thing else is the n. We have 1 over n squared. 1 over n squared. Okay, so that's what this gives me right here. You'll notice I have up here an m e to the eighth. I have a 4 pi epsilon naught to the fourth, h bar to the fourth, c squared. So why don't I bring the n squared over here to this side, n squared. And why don't I replace all of this with that right there. So I'm going to replace all of this with this right here. And I'll carry the minus through and just flip this right here. So it looks like delta E is equal to, well, everything in the circle is this, alpha squared E sub n, n squared, all over 2. And then since I brought the minus over, I'm going to swap the order of that. So that becomes 3/4 minus or plus L times L plus 1 minus J times J plus 1 divided by n cubed. Well, I have an n squared up above, so it's really just 1 n down below right here. But let me make it n cubed. So we got an n cubed L times L plus 1 times 2L plus 1. Actually, this n squared over n cubed is just an n in the bottom. N in the bottom. Okay. Now, this is going to be this. So this is how much the energies are going to be shifted. You notice it depends on L and J and what n is right there. Matter of fact, if we wanted to look at it for a particular case, any of these lines right here, suppose we just picked one like how about this one right here? How much does that line shift by? Remember, it used to just be at E sub 2 right here because that's the n. So it used to be, when n is 2, it used to be minus 13.6 over 4. That was the energy of the line. But now, how much does it just change by? Because this is just how much it changes by. Well, if we're going to pick this one right here, let me just circle this so we know which one we're picking right there. We get delta E, and we're calling that the 2p1/2 state. That's going to shift by this number, alpha squared, E sub 2, which is this one right here. I'll just call it E sub 2. Divided by n is 2, so that's divided by 4. And then over here we get 3/4 plus L, but we already know we're in the P state, so that's L equal 1. 1 times 2 is 2, so it's plus 2. J is this number down here, 1/2, so it's minus 1/2 times 3/2, which is minus 3/4. Oh, that's nice. Divided by L, which we said was 1, so it's 1 times 2, and that's 2 plus 1, which is 3. Okay. The 3/4 drop out. The 2's drop out. So everything inside this was just 1/3 or 1/12. So it'd be alpha squared over 12 times your E2, which is minus 13.6 all over 4. This term alpha squared, remember this is a very small number. This is 1 over 137. And so you're squaring that. So that's less than 1 part in 10,000. Just this is like 1 part in 10,000. So if you calculate what this is, I think I calculated what this came out to be. And it came out to be 3 times 10 to the minus 5 EV. Remember, this thing, this line is at about 1/4 of 13, which is, let's say, 3 EV. So it used to be at 3 EV, but it shifted up just a tiny amount. How much? 3 times 10 to the minus 5. Not enough for you to see that unless you really look in detail. So and for all the different J's and L's and stuff, they're all splitting these lines up right here, which is due to the spin orbital coupling, but this is the beginning of this anomalous Zeeman effect. But I should say this isn't the end of the story right here. This isn't the end of it right here, because there is another effect that's about the same size as this one. And if I'm going to correct the atom for the spin orbital, I've got to do it for something else that's about the same size. And what is that? Well, remember when we did H right here, remember H is P squared over 2m plus U. That's so this is just the kinetic, 1/2 V squared. There was our kinetic energy. Well, we know that this isn't, that's the kinetic energy is only true when you're going slow. We already know when you're going really fast, that doesn't work for the kinetic energy. You have to use, what can we say? What did we say, the kinetic energy? Didn't we say it was, how about if we say it's the kinetic energy is the total energy minus the rest mass energy, mc squared, where the total energy was the square root of p squared c squared plus m squared c to the 4th. That's minus mc squared. Remember, when we looked at the hydrogen atom, we calculated the speed of the smallest orbit, and it was 1/137th of the speed of light. Well, and so even that 1/100th of the speed of light affects this right here. And so if we're going to be this exact, we have to put into account this better kinetic energy, not this one, but we've got to put in this one, which makes about the same size effect. And that way, when we combine this effect with this effect, that'll give me this, they call it the fine structure, but a little bit closer to the true atom. Next time, we'll put in the correction for this better kinetic energy. Okay. So we have one correction here. You remember what we had was this change in energy right here, and we wanted to simplify all this right here. And so we had calculated alpha, this was our fine structure, and this was our E sub n, which is right here. And when we multiplied these two together, what I did is I left off that 2 right there, and I needed to put that 2 back in there. So that means that when I plug this up into here, there won't be a 2. There just won't be the 2. It'll be gone right there. And so it should have just been this without the 2. And then I just wanted to do one last thing. Since this is 1 over n, I think I decided to put it as n over n squared, which is the same thing. And I pulled a 2 out of these two right here, this 2l plus 1, which made it L plus a half, and I pulled that 2 out. So just wanted to correct that.